Okay. After some failed tests trying to get this started, I think we have an actual stream going. So welcome to my office hours. I'm a Ph.D. student, or am I a candidate? I've passed my candidacy a while ago, so I don't know. I should know the terminology. But I decided to start hosting some office hours in the mornings while I have my breakfast and have my coffee. And yeah, so the general idea is, you have all my streaming information there. Amateur hour. Let's open it up to this. So yeah, the basic idea is just that you all, talk about things I'm learning. Here's this book on infinity categories I was looking at a little bit over the reading week break. But then if, people jump in the stream and people have questions, for example, then you can, ask me questions during the stream, and maybe I'll answer some of your math questions. How do I set this up so I see chat? Probably no one's going to be in this one because I didn't tell anyone this is happening. I just randomly started this stream, so this is more of a test. Yeah. Well, with that, I guess let's look at the internet. Let's go to Math Reddit and take a look at some of the math news today. I'm a student discovering mathematical research. Okay, let's look at this. Let's take a look at what this person's saying. So, I'm a student currently discovering the world of mathematical research. I'm astonished by how difficult it is to find specific theorems or results. Yeah. True. It feels like everyone publishes their articles in their own corner with numerous references, making it very hard for someone to explore a new field to understand it. I've spent hours searching for the proof of a theorem because every article keeps referring to many others endlessly. Yeah, so a couple things here. One thing that comes to mind, actually, okay, this should not have happened. This is maybe a bad example, but there's a famous example. Oh, hi, there's people in chat. Wow, nice to see you. Let me know if you have any questions. But, so I'm just going over this Reddit post. Yeah, there's this famous example of, there's someone who is in, biology or chemistry. I forget the name, but she basically, reinvented the trapezoidal rule from calculus, right? But, of course, how would you know, if you came up with this rule, you wouldn't be like, I'm going to call this rule the trapezoidal rule. Maybe you would, because of the shape, but, it's very believable that you could have a hard time finding this result. So this is, this definitely happens. Anyways, let me keep reading what they have to say. This led me to think about a Wikipedia for research, where every mathematical subject would be included, gathering all known results that would be linked by the fact that one follows as another. That way, discovering new topic, one could start from the very beginning and progress step by step. I know this idea might seem naive. I'm curious to hear your opinions on it. Would also love to receive advice from someone who's been in my situation before. So actually, this kind of already exists in some sense, at least in limited ways. Maybe not for all of mathematics, but for example, there's what's called the Stacks project. Maybe I can look it up. So Stacks project, right? So there's this whole website, the Stacks project, and yeah, it's basically for algebraic geometry. There's all of these chapters, and people are constantly working on it, adding to it. Of course, this is very, very far from research level theorems, what people are doing on the cutting edge. But this information is, but people are starting to like sort of build these libraries in a more systematic way. So that definitely exists. There's also, well, I wouldn't say NLab is exactly doing the same thing, but this is also a website that's trying to like gather information and has links to stuff. But you know what, actually, as I'm thinking about it, it's less along the lines of what this person's suggesting here. There's also, what is it, Caradon? Yeah, so I think, did Jacob Lurie found this or start this, or was one of the organizers, I think? But yeah, so as it says, an online resource for homotopy coherent mathematics. So it's kind of like doing the same thing, but I guess for infinity categories, I thought maybe it was more general even. Wow, I should look at this. I was thinking about some infinity category stuff lately. So that's cool. Yeah, so this already exists. And it's interesting, you know, I was actually having a discussion with a friend of mine who's a postdoc a while ago, and he shared this same sentiment about being, frustrated about how hard it can be to find specific theorems. And it's also, part of the difficulty is that there isn't a uniform language, right? And the problem is, it's hard for there to be, like, we try, you know, as like time goes on, and we sort of work out the best way to phrase things or not. Eventually we land on sort of standardized languages, usually, but not always, right? There's different people in a given field that have different language for stuff and different ways of talking about things. I mean, it's the language of mathematics, like, is like any other language. So it's going to be subject to the same, like, new terms and slang and whatnot are constantly going to be evolving. So in some sense it's unavoidable. But, you know, one of the cool things we talked about was the possibility of, so there's if you don't know, there's these things called proof assistants where let me just bring one up. So there's the natural number game. So there's these things like lean, and there's other proof assistants. There's a whole bunch. So if you go to this really cool website, you can sort of play an online version that gets you used to proving things. So we can play the set theory game, right? And then basically what it is so you're trying to prove theorems like this, and then you type stuff into the computer. Oh, so you can see a previous thing that I proved here, I guess, right? So have H4, right? So I used some sort of was this a previous one I did? Oh yeah. So I used the fact that X is in what did I do? No, I shouldn't try to explain things when I'm jumping into old work from whenever ago. Anyways, the point is you formalize mathematical proofs, and the interesting thing about this then is that means you're also formalizing statements of mathematical theorems in terms of these symbols, and so one of the interesting possibilities is that you could set it up in such a way that it's someone they said off-topic question, but then they retracted it. But you can definitely ask your question. I'm going to finish this thought though. Anyways, one of the interesting things is that if we formalize mathematics in this way, in a way that the computer can search, then it could easily search the database. And of course, we still have this same issue that if you're looking for like exact wording, like different people might think to word a certain theorem a little bit like slightly differently. nonetheless, the computer can still search through the database and try and like bring suggestions to similar theorems. And so that could be a very useful tool even as like a research mathematician, because you could be like, oh, I wonder if this result exists. And if it doesn't, you could at least find like similar results. And I mean, the dream would be some sort of citation for where it originally appeared as well. But even if it's just in the Lean library, then you could be like, oh, look, there's a similar result. And that'll at least give me an idea of how I would prove my similar thing. But, you know, in that case, we're very far away. We're very far away. Okay, so someone in chat asked, can you talk about your experience on writing my thesis? I'm writing my undergraduate thesis. Yeah, so I actually have written. So I can tell you about my PhD thesis, but I also wrote a master's thesis. So I can tell you a bit about the experience of that. I'll pull it up here. I'm a little bit embarrassed by it in some sense. I think the mathematical content is good. I'm like fairly happy with it, but some of the writing skills was not great. Like the whole tech document, there's no indents on like most of these paragraphs. So that's a little bit embarrassing. But I think the content was cool. So I'll tell you a little bit about how the writing of my thesis went. So the interesting thing is I actually got started on my thesis early, which is maybe an atypical situation. So maybe I won't talk about that part, because that's I'll maybe keep it more relevant to you. So yeah, a lot of the time. So this is different from an undergrad thesis, but you know, the first good chunk is just like, as you probably already know, is just trying to learn, you know, what all these words mean. So you see, oh, there's all these like fancy words and symbols, blah, blah, blah. And it just takes a long time. Like, you know, the sort of main tools in my thesis were vector bundles and Lie algebras and representation theory of Lie algebras. So first I had to go and like learn the language and learn the basic theorems, and I had to spend a bunch of time sort of reading up on what all of those things were, and that's kind of reflected in the thesis. So probably, you know, much like the early parts of a master's thesis, your undergraduate thesis. Oh, holy crap! There's someone in the chat I haven't seen in a very long time. Good to see you, Russ. Good to see you. But the writing the first part, you're basically just going to be like repeating basic theorems here. So like you see this stuff I'm proving, like this is a proof, like derivation, definition of these things. Like this is all like, it appears in like a basic differential geometry textbook, right? So a big chunk of your thesis, most likely, especially undergrad thesis, you're probably just going to be repeating a lot of stuff that's already known. But of course you don't want to be doing plagiarism. You want to be putting this into your own words and sort of finding your own. So that means deeply understanding these statements, right? Because you basically, yeah, you might be guided by the proof in a textbook, but you want to put it in your own words, right? You want to understand it in such a way that you could re-explain it to other people. Now it is possible. I don't know, you know, how your thesis is going. It could be there's something original in there. Certainly some fields are more amenable to that than others, but in either case, oh yeah, here's something. I'm gonna like, oh, I should do a whole stream where I rip apart my own thesis. But by the way, if you have commuting diagrams, I'm a big fan of putting everything on the outside of these arrows. So to me, this looks gross, putting these on the inside. I like everything on the outside these days. But anyways, yeah, the actual writing process, of course, is the least fun, right? Typing up, God, these symbols look so cool though. but actually, typing up, once you've done the work to understand things and scribbled it out on paper or a blackboard or a whiteboard, writing up the details is maybe like not as fun, although it's fun in its own way. I kind of like the careful placing of words and whatnot. For me, it was kind of nice because when I was writing up my thesis, I basically was doing this over the summer of COVID. And so basically everyone was at home anyways. And so I was like, well, I'm stuck sitting at home, so what am I going to do? I also was living in a nice place that had a nice little French porch. So I would I'd make my little French press of coffee every morning. I'd go sit out on the porch. The birds were singing, and I would just sink into some math and write up these details. So yeah, it was, in some sense, it was really nice actually, because it was like I had nowhere else to be. I had nothing else to do. I imagine that Nicole, who asked the question in the chat about writing up the thesis, I imagine it's a little more chaotic for you, right? Because if you're writing it up right now, you're probably taking courses. Those are probably like fourth year undergrad courses and probably some maybe even grad courses. Some background, probably nothing original. I'm finishing to study the topics, which are in geometric group theory. Cool, very cool. And some topological methods on group theory. Very cool. Yeah, I mean, definitely, in some sense it would be like, it's rare that in a undergrad thesis you would be doing something original. Well, depending on the field, right? I mean, definitely, topological group theory, geometric group theory, topological methods in group theory. This is a well-trodden thing and maybe an advanced topic. So, it'd be hard to imagine doing something really new there. But yeah, 4 courses. So yeah, definitely difficult. But the nice thing is, if you are at the writing stage, where you're mostly, it's like you've done you've put in the work, the brain power to the learning, and you're just sort of, trying to get all the details in there. It can be nice as a change of pace. So like, let's say you spent a bunch of hours studying or something for your courses, and you're like, okay, well, I have energy. I feel like I can still be productive. It can be a nice way to change gears for a little while, which is I think a good word of advice, generally speaking, for like mathematicians at any stage, is like, always have a side project, or have like more than one thing on the go at the time, because like sometimes you'll just get stuck, right? And you'll be like, I have no idea how to like progress on this homework problem or this research problem or whatever it is. And it's always good to have at least one other thing, so that if you still feel you're like, oh no, like I'm in the zone, I'm locked in, so I don't want to like go do something else right now, but like I'm also losing my mind about this theorem. It can be nice to have that. But I also know, like, as a procrastinator, like, there's this weird paradox where I do less when there's something I have to do that I don't want to do. So like last night, I have some marking to do for an algebra assignment, and I didn't really want to do it. And so I actually ended up doing, like, if I had just worked on something else instead, like on my thesis project, I would have at least gotten something done. But I basically just sat there being like, oh, I have to do this thing, I don't want to do it, I'll just distract myself with like YouTube or playing some music or something. And then like I got less done. So yeah, it is like that sometimes. Yeah. Anyways, so yeah, wow, we've covered a lot of stuff in this very short office hour. We've been productive. advice, Thesis, the lean 4 game, Carradine. Yeah, pretty sweet. I think my normal timer for office hours will just be until my coffee's empty, and it normally takes about an hour. So I wonder what other people have said about this. Spent hours searching for a proof of theorem. That's unusual and bad. Oh, we got some more comments here. For my bachelor, I need a 4-week internship. Oh, a 4-week internship. Which type of work is interesting to a pure mathematician? Yeah, so on that, yeah, for your bachelor, you need a 4-week internship. That's interesting. Is it like what kind of bachelor is it? It's not in pure math? Are you doing something applied? Because I've never heard of a pure math bachelor where you have a 4-week internship. Wow, hello from Japan. Hello. Yeah, what type of work is interesting to a pure mathematician? I mean, there's a lot, right? So first off, like the pure applied divide is very loose and wiggly in some places. So there are pure mathematicians that are very close to being applied, and ones that are very far. And then also on top of that, like, I feel like even within pure mathematics, the genres of math are as varied as genres of music, right? Like you have people that like all kinds of music, but you might have people that only listen to metal or only listen to K-pop, and that's the same thing for mathematics. Graph theory is can be very, very different from harmonic analysis. And some people love both. I do. Some people don't like either. So it's a little difficult to say. Yeah, if you don't like the idea of having to do statistics, actuarial, or programming, I mean, yeah, there's so much. Oh, and we got Greece in there too. Hello. Hi. There's so much that you can do with outside of all of those areas. But let me tell you something from my own personal experience. And I'm a pure mathematician. I do very, very pure mathematics. But, and from Brazil. Oh, Nicole's from Brazil. Hi. Wow, we got a whole, I don't know if I've had in any of my in-person office hours this many people from across the world. But what was I saying about the... Yeah, one thing I regret, actually, is not trying harder to like statistics and programming when I was younger, because... Guten Tag. Guten Tag. Because I really hated statistics when I was in my undergrad, and now, on the other hand, I appreciate it a lot more, especially as I think, maybe going to industry instead of academia could be an option. But not even that. I've just come to really appreciate, bonjour, comment ça va? I've just really come to appreciate, though, the power of statistics and programming. So I would try and find a way to like it. That's what I would say. I would advise you to try and find a way to feel like it. If you can't, you can't. Some people just don't like broccoli. I do think you can force yourself to like broccoli if you just force yourself to eat it for a month, and it would be good for you. And I think the same thing for statistics and programming. I wish I tried harder to like it when I was younger. So, we've got a question here about why is there so much info online about series and infinite products, but almost none about infinite power towers? That's a good question. Off the top of my head, I mean, I think it's just partly because products and infinite products and infinite series are just more common. They show up more in the mathematics that humans tend to do. It's maybe, less often that we would see such a thing. I also wonder too about convergence of infinite power towers. Like maybe I'm just guessing here, but maybe the conditions on convergence are a lot more stringent, like a lot more strict, I guess I should say. So maybe there's just less interesting examples. Not really sure. Basically conceded that it's going to be in statistics programming fields. So, maybe one thing I can say about if you currently are having problem like enjoying statistics or programming, one thing I'll say about that is about how I came to enjoy it. So I ended up, a common, core thing you should learn if you want to be a mathematician in the broadest sense of that word, or just interested in mathematics, is measure theory. Part of any good analysis sequence, certainly by the time you get to grad school. And that was kind of the gateway drug for me to learning about statistics, is because sort of when you go to continuous statistics, that's sort of the theoretical foundation for it is measure theory. And that all of a sudden I found, I was like, wow, there's interesting theoretical questions there. And that was sort of the first time that I started thinking about statistics, and I was like, oh, interesting questions about probability. If you throw a dart, you imagine throwing a dart at the closed interval from 0 to 1, then you can, the probability that you hit any one number is going to be 0. But, of course, you hit a number anyways. And so, thinking about these interesting, what does probability 0 actually even mean, and things like this. Also, by the way, so jumping back over to my master's thesis, so you can see, it was all this crazy theory stuff, but actually, here's a bunch of code. So even though the topic of my thesis was very theoretical, it was about representation theory and stuff about manifolds and whatever, you can see, actually I did a whole bunch of code in Sage because I more or less, there was some sort of to not explain any of it, but there's something I was trying to prove that depended on two numbers, P and Q. You can see these two numbers here, something about some representation or whatever. But the thing is I had some theorem. If you look in the body of the thesis, there's some theorem that says, okay, if you know it for a given P and Q, and P is at least as big as some quadratic term in Q, then you can apply an induction proof that shows it for that fixed Q for all the larger P. But the problem is you need those base cases. And outside of the case P equals 2, Q equals 2, that's actually already pretty big. It's very hard to do by hand. So actually you can see in the tail end of my thesis here, I do some, I think I crunch an example for P equals 1, Q equals 2 here. I do a very concrete computation. And already it's messy, it's involved, there's a lot of variables. And so the code, I didn't think my thesis was going to be about code at all, but then my supervisor was like, yeah, maybe you can write some code to get these base cases, and by doing that code, I was able to crunch the code, those established some base cases, and that actually proved some infinite families of results. So I think sometimes the way through, and that sort of got me more interested in programming. So sometimes the way through is to find a thing that you care about, like that. Or actually, I don't know. So one thing I was doing over the winter break, I was doing. I'm a musician as well. I don't know if you can see in the corner of the screen some guitars behind me. What is this file? Where is the file? I don't know. Well, anyways, I started doing some like programming about like music theory and notes and modes and chords and like, I was like, oh, maybe I could like, write a program that will like, I'll feed in a note and it will tell me like all the chords in that scale or something like that. So I think one of the ways through is like you can find ways to even connect it to like theoretical math and your interests. Okay, hi, I have a question. I don't have an intuitive way of dealing with the objects that are defined in algebra. I think of modules as a ring of endomorphisms that preserve abelian structure. How should I try to do algebra? That's an interesting question, yeah. Is it even worth trying to justify the intuition behind, or accepting it is better without questioning? That's what my profs told me anyways. Yeah, I mean, so first off, yeah, I had someone else in my algebra tutorial the other day who shared a similar sentiment. They were a student in my analysis course last semester, and they said to me, they're like, oh yeah, analysis, I find it much more obvious and intuitive, and like in algebra, I don't even know how to start the proofs. And part of this, I think, is there's some sort of, for whatever reason, I don't know if it's, nature versus nurture. Of course, everything's a combination. But it's for some reason, some people are just have more of a mind for analysis. Some people have more of a mind for algebra. Now, I'm not saying that to say be defeatist and give up and just say, oh, I'm not an algebra person, because I think you could just put in the work and maybe you become a both person, right? But I definitely think it is worth trying to find the intuition and how to come up with that intuition. I mean, well, the only two ways to learn math is to read math and write math, right? So sometimes just grinding through a bunch of examples will slowly build up your intuition, like doing a bunch of exercises, but also reading, right? Different people have different perspectives on mathematics, so it's good to consult maybe several different textbooks, and sometimes authors will explain a bit of like how to think about things. Yeah, so for me, I guess I am more of an algebraist, so it's harder for me to give advice about if you're struggling with algebra, because I like thinking of these sort of structural objects, rings and kernels and taking quotients of kernels. But I wonder if I can open OneNote here. Maybe we'll talk a little bit about modules. So the classic example, of a module. How do I want to close this thing? Yeah. Anyway, so like the classic example of a module would be, oh, my writing pad isn't plugged in. Now bear with me for a second. Oh, I have, right, okay. So yeah, the most like basic thing about a module, like the classic example, is to just think about z to the n, right? Now, of course, you need to be careful to not get too used to this example, because it's sort of unusually nice. But it's very natural to think of like you think about R2, right? And it's just the set of all. You've got these coordinates, elements, and it's a picture, like just R2, it's just the real plane, and we're thinking of this as a vector space, right? So we can add things and we can scalar multiply things, right? With modules, the question is, okay, so yeah, we can imagine like R2 in this vector space, but then, we could consider all real numbers, or we could consider when both of these coordinates just lie in some special subset. And if instead they lie in some special subset, say the integers, I would say it's pretty special, well, geometrically we get this picture of it just being all of these dots, right? Just all the integer, just all of the pairs of elements that have integer coordinates. And then the interesting thing is that you notice, well, if you add like a pair of coordinates that have integer coordinates, that will still have integer coordinates. And if you multiply, if you take the scalar multiplication, where again you restrict your scalars to integer coordinates, that new thing will have integer coordinates. And so, this in some sense is a very natural thing to consider. And then quickly you say, well, okay, I mean, is this really special? Is this really a special thing about the integers and the real numbers? I mean, or is this part of a sort of greater phenomenon? Can I sort of study a bunch of these examples all at once? And one thing that you notice is that, well, the integers are an example of a ring, whereas the real numbers are an example of a field. And so you realize that if you look at like Wikipedia, maybe I'll pull it up here, so look at like vector space axioms. So you go check these axioms of a vector space, right? And everywhere here, we say that our scalar has to belong to some field, okay? In linear algebra 1, you just work with the field of real numbers, maybe the field with complex numbers, but actually it can be any field. But pretty much nothing in here really requires it to be a field, in the sense that nothing really requires it to be, well, even commutative, for the scalars to be commutative or to have inverses. And so you say, well, what's the most general version of this I can talk about? What do I really need my scalars to have? Well, I need them to have some form of addition, and I need them to have some form of multiplication. What are structures that have addition and multiplication? That's a ring. And so all the definition of a module is, so I should say one definition of a module is you just take these vector space axioms, and everywhere where you imagine that your scalars belong to a field, you just instead say that this belongs to a ring. And that is equivalent to the definition of a module as being the endomorphism ring of some abelian group. So that's actually a really great exercise, is to prove the equivalence of definitions. In fact, I think this is even an exercise in Alofi's book. Yeah, so I highly recommend doing that. The definition in terms of like axioms of vector space, way more intuitive, I would think. But then the other definition in terms of endomorphism ring of an abelian group is maybe more systematic and formal. And it's always a good idea in mathematics to be able to flip between the systematic and formal way of thinking and the intuitive way of thinking, and know how to take intuitive facts state them formally and rigorously, and then conversely had to take formal, rigorous facts and reinterpret those as intuitive statements. Anyways, I think that's going to be it for today. It's been around an hour. My coffee's almost empty. Yeah, it's been great chatting with everyone. So nice that there's people from all over the world that stop by this office hour. You personally think of algebra, classification of functions, operators on spaces. Yeah, I mean, that's definitely one part of the perspective. If I see you in the next office hour, maybe we'll chat about the cool ways in which that inspired, that perspective in functional analysis inspired algebraic geometry. I'll say, I don't know when all my office hours are going to be. I'm going to sort of do them sporadically. I know I should be on a schedule if I want people to attend regularly, but I will probably sometime around like 7:30 Mountain Time, at least like 3 days a week, maybe more, maybe even tomorrow. Oh, nice. So many great comments, but I really do have to go. But hello everyone. Unfortunately, yeah, I'm not gonna review a module again right now. But if I see you in a future stream, I would love to tell you about why we care about modules. So, anyways, thanks again, everyone. Gonna kill the stream.